Okay. Now I assume everybody has a experience on the error correcting code part. Okay, then as I mentioned, I'm not happy with the ordering of these problems. So for me, problem 4, 5, 6, 7 should be harder problems that goes after 8, 9, 10, maybe 11. Okay, because problem 8, 9, 10, 11 are dealing with a concrete example. Okay, and then 4, 5, 8 are doing abstract theory. So if I were you, I will firstly go to problem 8 and then do 9, 10, 11. Get familiar with the story. Then I'll come back to the 4, 5, 6. I think a lot of people get stuck at the 4, 5. Okay, we are going to skip it for now and then directly go to the example. That's my preferred way to do this worksheet. Okay, but the story are the same, exactly the same. And then you probably get a lot of hint from problem 8 and 9. Okay, for problem like for 5. All right. Let's do problem 8. All right. So I will basically tell the story for that. Problem 8 and 9, let's see. Rough idea. So first of all, we are sending something out, right? Okay. Maybe you guys can look at my screen while read the project problems. Like I suggest everybody go over the problem until the end. So we should read through all the problems until problem 12. Okay, then the rough idea is the following. So we want to send a message, right? We have a sender. Okay, in this concrete example, the sender have a 5-digit code. And then they are going to write the code as a 5 by 1 vector, which is denoted by X. Okay, let's follow the project notation. Okay, then if we send a plain code like this, we are not going to have the correction function. Okay, because if your information has no redundancy, then if it is an error, it is an error. Okay, in order to have the correcting part, we are going to add some redundancy there. Okay, so the way the sender adds the redundancy is multiply this code by a generating matrix called gbig. The gbig is 9 by 5. Okay, which is on page 2. So you can see a very concrete gbig, right? Okay, so then after that, the receiver is going to receive a y vector, which is 9 by 1. Okay, so then we have 4 redundant digits. That's going to be our correcting part. Okay, because we have redundancy, then if there's error, we are going to detect that or even correct that. Okay, so any questions at this stage? All right, if no question, let me come to the receiver side. So what the receiver is going to do, of course, he wants to recover the 5-digit code, right? Because this is the information. Okay, then detect whether there is an error or even correct it. Okay, the receiver is going to have a H matrix called HBig. I will tell you guys how to get the pair JBig and HBig in a second. But now let's assume we have a correct one. Okay, then I'm going to multiply it by Y. All right, so then Y, remember, is 9 by 1. And then HBig is 4 by 9. Okay, so then you are going to get a 4-digit code. All right, so the upshot is the following. If we get a 0, 0, 0, that means we receive the correct code. Okay, but if we instead get a for example, 1, 1, 1, 1. Actually, anything other than 0, 0, 0, 0. That means we have an error. Okay, so firstly, we are able to detect whether there is error or not. Then in the problem 11, we are going to find a way to detect where the error is and how to correct it. Okay, so question 8 and 9 are about the encoding and decoding process together with like a detecting error process. Okay, problem 10 and 11 are about the correcting process. Okay, any questions so far? That's a rough idea. Now I will tell you the mathematics behind this. Okay, questions, good. What do we mean by the error? Okay, that's a good question, Ben. If you look at the big picture on page 2, you have an encoder, right? So in our language, we have a sender. Okay, we have an encoder process. Then we have a detector, which is the HBig side, the receiver side by our picture here. And then what I didn't draw is we have a channel. Okay, there might be noise in our channel, so which may cause some error in the message we received here. So basically, the Y matrix, the Y vector we received might be different from the encoding message because we have a sending process, we have a communication process. Okay, good. Okay, great. All right. So that's actually a great point because that's closely related to the mathematics. Okay. Nice question. Okay. So now problem 8. What's the mathematics behind this? First of all, the pair of matrix are chosen in this way. GBig is 9 by 5, right? And its image has dimension 5. Okay, because we at the most have 5 column vectors, right? And then they span a 5-dimensional vector space. They are linearly independent. You can check. Okay, then my kernel of H is like 4 times 9, right? And then if you solve that, we have 9 variables, 4 equations. Then by default, the solution space has 5 variables, right? That's how we call the dimension equal 5. Okay, maybe I always mention the dimension word, but we still haven't seen a rigorous definition. But now it should be clear, right? When we talk about image and kernel, that should be clear. Okay, so the point is this pair are specially chosen so that we don't only need the dimension to match. We also need the space to be actually equal. Okay, meaning that I don't only care about dimension. Okay, we also require that the image and the kernel are actually equal. Okay. So that's the point for problem 8. Maybe if you read the problem 8, you don't see an image of G big, right? You probably say something like Wei Hamming. That's actually why I don't like the ordering of the problems. So in our practice, image of G big should be the same as Wei Hamming. Okay, so, and I guess this is true for any this kind of encoding process, because we are always going to make a matrix as a generating matrix. So our space of Hamming code is always going to live in the image of a matrix. Okay, so that's how you construct the H big. All right, the H big in our project is called a parity check matrix. So basically, you want the kernel of the parity check matrix to be the same as the image of your generating matrix. Okay, does that make sense? Then the point is, once you receive a Y, right? If Y lives in the image of J, that means we are getting a correct message. Okay. I mean, so there's still a problem here. We have an assumption, like at the most we have one error or one digit noise in the channel. Okay, that's an assumption we have to make. So with this said, if Y lives in the image, if Y lives in the image of J, then that's the correct message. Then by this construction, image J equal kernel H. That means if we multiply H with Y, we should get a 0 vector. Okay, that is clear now, right? So I think we are able to answer problem 8 now. So if you guys have these arguments there, especially this core part there, I think you are okay with problem 8. Okay, so any questions so far? If not, I'm going to move on to the actual solution of problem 9. Okay, because we are recording this, I will basically clear everything. All right, so now let's say problem 9. So first of all, those several cells are basically generating a H matrix. Okay, so that's our H big matrix, copied from the product file. All right, then let's read the problem 9. So, for example, we received 3 vectors, 1, 0, 0, 1, 1, 0, 1, 0, 1 for the first one. So I had it here. Okay, and then the other 2 I had it here. All right, so how do we tell whether or not this is the image of G big, or whether or not there is a error? So basically, we are saying that we just multiply this thing by H on the left, right? So then if this is 0 vector, that means there's no error. Okay. Or this guy lives in the image of G big. And then on the contrary, if we have a second vector like this is the second vector. Okay. And then I multiply it by H big. So we get some vector that's not 0, right? That means this vector does not live in kernel of H. So remember, kernel of H is image G big, right? So that means it doesn't live in image of G. Okay, similarly, you can do the V3. V3, I bet you are going to have still a non-zero vector. So meaning that the third vector is not in image of G. Okay, that actually matches the statement of the problem. We only have one vector that's in the image of G. Okay, so meaning that we only received one correct message. Okay, so let me stop here and point out the following. So that problem 9 is actually very inspiring for your problem 4 or 5. Okay, for your problem 4, a lot of questions appear in office hours. Is the following: shall I regard the 7-digit message there? Code word, okay, in their language. Okay, so I received, for example, a 7-digit of zeros. Okay, code word. Then should I write it as a row vector or column vector? Or the same question is asking whether my G Hamming is a 7x8 or 8x7 matrix. So that question 9 actually gave you the answer. Okay, we are actually regarding this vector V1 here, or the code word here, as a column vector. Okay, so even though it's presented as a row, right? That's because of our writing system. But what really happens is we have a 4x9 H big, and then we are writing a column vector here, 1, 0, 0, 1, and a bunch of rest. Okay, so that's the correct way to present the matrix in your problem 4. Okay, inspired by problem 9. Okay, that's why I suggest firstly do this example. Okay, any questions about this? All right, so now let's move on. We have a problem 10, 11, and 12, right? So problem 10 is relatively easier. So it's asking, if I have a y, okay, how do I get this x, right? Okay,